Washington State University. Go Cougs!
Hello and welcome back to the course on statistical inference. We're in Module 3 where we are discussing dimensionality reduction and clustering techniques. And in Part 2 of this module, we'll be looking at the principal component analysis approach to dimensionality reduction. Principal component analysis, or PCA, seeks to reduce the number of features that we are using to describe our problem or our data. So our data may originally be expressed in terms of D features, and we want to reduce that down to D prime. But specifically, we are looking for features that maximize the variance, because higher variance features generally improves learning performance. For example, if you look at the 2D plot of these points expressed in the original dimensions D1 and D2, and we see that the points tend to vary along the slope equal 1 direction and slightly less in the orthogonal direction. So if we were to run PCA on this data, PCA would likely identify those two dimensions as the new dimensions. Again, because the variance is highest along those two directions. So we would re-express our features in terms of D1 prime and D2 prime. Or if we wanted to reduce the number of features, we may just go with D1 prime. Again, in general, this is most appropriate when you have hundreds to thousands of features and you need to reduce that to improve the learning performance. Another useful aspect of PCA, a practical one, is simply to be able to visualize the data. If you have a high dimensional data, you can't really plot that on a screen too well, so PCA can reduce those dimensions down to, say, 2 or 3 in order to be able to visualize them better. So as an example of running PCA, we took our 9-dimensional sensor data expressed with 9 features, and we used PCA to project that down to 2 features, and then we plotted the result. So we see a couple of screenshots of that result, but let me actually pull up the plot. So that's in the file plot2d Python. So if you run that, again, it is projecting our 9-dimensional feature space down to 2 dimensions. And these are the 2 dimensions that we're using for this plot. So at first we just see mostly the play examples, but we do see that they're spread out fairly nicely in both of these dimensions. And so that's really what we were going for, not only just to be able to visualize it, but to improve the variance along the dimensions that we compute. Now if we wanted to go look at the work examples, we'll need to zoom in a little bit. So I'm going to zoom into our work examples, and so there you can see the work examples. We've zoomed in quite a bit. In fact, I can zoom in a little bit more interactively here. So again, you can see in both directions there's significant variance. We don't have all of the points clumped together along one of the dimensions. So even within the work points, we were able to increase the variance a bit. So that gives you a flavor of how PCA works, especially in terms of visualizing the data. And I'm not going to go through the code in that file. You can take a look. It's a pretty straightforward way of running PCA and then plotting the points. So let me go back into the notes. So as I mentioned, our main goal is to be able to improve statistical inference by reducing the dimensionality of our data, and that's the main purpose for using PCA. Also, as I mentioned, most learning algorithms tend to run in time proportional to the number of features you use to describe the data. So by reducing the number of features, we have the added benefit of reduced runtimes. So in terms of learning and classification performance, PCA gives us fewer features, and they're usually higher variance features, and that can improve overall performance, both in terms of accuracy and running time. So let's see this in action. In the PCA.py file, you'll see a use of PCA for reducing our 9-dimensional sensor data feature vector down to 2 dimensions and looking at the results of naive Bayes in both cases. So first, we input our usual modules, but in addition, we import from the decomposition module the PCA class. And again, PCA has a few parameters, but the main one we'll be interested in is the number of dimensions, or the number of features that we want to project to. So in our case, we're going from 9 dimensions down to 2 dimensions, but of course we can change that to see its effect on performance. So this part is fairly standard. We've seen this before. We're reading in all of our data, creating an instance of the naive Bayes classifier, fitting that classifier to the data, and then using that classifier to predict the same data, looking at the accuracy of those predictions and printing them out. Then the next stage, we're going to run the principal component analysis. And so much like we run a classifier, we'll create an instance of the PCA class and pass in the number of dimensions that we want to use. We then fit the PCA method to our data, and then we use that transform method that all of the different dimensionality reduction methods have, that takes the original data and then transforms it to new data, where it's essentially just including the specific dimensions that we've computed. So now that we have our data re-expressed in terms of these new dimensions, we again use a naive Bayes classifier to fit to that new data, use the classifier to predict that same new data, and compare those predictions to the original correct predictions, and then print that out. So here you can see the results of running this, and let me actually run it for real. So this is in the PCA.py file. So if we run that, so here we see the accuracy before running PCA and the accuracy after, where we've reduced the number of features from 9 down to 2. And as you'll note, we didn't get an increase in accuracy, but the accuracy did remain the same, and it achieved that accuracy with only 2 features. So definitely in the situation where you have hundreds to thousands of features, being able to reduce that down to just a few features and still get the same accuracy is going to be a benefit. But in experience, again, with larger data sets and more dimensions, doing the PCA approach to reduce that will actually generally improve the accuracy performance as well. So that's another method you can use to reduce the number of features. And next, we're going to look at a technique for just trying to make a better understanding of our data by identifying groups within the data that are closely related. And that technique is called clustering, and we'll be looking at that in part 3.